Welcome back everyone. So, we are studying NPTEL course on topological phases of matter. So, we are now starting model Hamiltonian and we are into 2D, and we talked about two special points in the Hamiltonian parameter space, and we talked about when D becomes equal to plus minus D3, but D1, D2, D3 do not go to 0 at the same point, which gave us the topological insulator. And if D3 changed sign, we had a Chern insulator. If D has a fixed sign, we had a trivial insulator. That is what we studied in the last class. Then we also saw that if you want to go from a phase transition from trivial to non-trivial, we have to go through a band degenerate point, and that band degenerate point happens at this point where all the 3D goes to 0. And now let us talk about this. So, there are many interesting things happens, and they are also topologically relevant, but not the same topological invariant that you can compute, because your connection and curvature diverges. But they can still be a stable degenerate point, and we have seen that experimentally. And let me tell you the details of those. We will call it topological semi-metal. And the criteria is D1, D2, D3, all 3 goes to 0 at K star. So, K stars are the root in the Brillouin zone. So, we have 3 equations to solve. So, it is called codimension. How many equations we are solving to get a degenerate point is called the codimension. So, 3 is the codimension. Of this problem. Let us call it C being the codimension. Now, interesting thing can happen depending on in which dimensions we are in. Let us start with even 2D, then we will come back to 1D, since we are talking about 2D. So, we actually have 2 parameters. Topological space of dimensions 2, that is why the D equal to 2. And what we are looking for, so in the Hamiltonian space it is 3 dimensions. So, the codimension is 3. So, it is not really a homeomorphism between those 2 dimensions. So, that is why in 2D case we will give you some point where the band degeneracy is happening, and let us say the band degeneracy is happening at the gamma point, this K star equal to 0. It does not necessarily have to be, and it is a Dirac cone along both directions, kx square plane, and this is my E. Okay, so at this point there is 0. And because you have 3 equations and 2 two-dimensional manifold, so this, so you have a redundant equations to solve, right? So that's why these Dirac cones are not stable, because you always have the third equations to unstabilize it. You just need because it is not a homeomorphism, so it is not a same parameter space from kx, k2 to d1, d2, d3. So always d3 or any other can gap them out. But you can have symmetry to protect such gap, protect the gapless Dirac cone. And for the case of graphene, we will see that it will be the chiral symmetry. And also symmetry will enforce this Dirac cone to appear forces the Dirac cone at high symmetry points, k points, such as here, 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 and their equivalent points. So in one day you just can generalize. So you have kx and d1, d2, d3, all three are present. So you have 2 additional equations, so it will be even unstable. So for SSE's model we looked into d1, d2, that was also unstable except some symmetry called chiral symmetry, which make those to be stable. The Dirac cone. 3D is trivial or easy because we have d equal to 3 and then you will have d1, d2, d3 equal to 0. So your codimension also matches, so it is a homeomorphism. So now you can have a Dirac cone, 3D Dirac cone at some point. You cannot really draw it, so you can have a 3D Dirac cone sitting here, which is linear in all 3 dimensions. Okay, so just a single Dirac cone. Now, in some cases, what can happen is that in 3D they do vanish, but this can vanish in a given plane or along some line, whereas this can vanish at given points. In those cases, the Dirac cone can split into being Dirac cone at some non-high symmetric point. They are called Weyl cones. Okay. And so here they match. So now we can take a counter example called Nodal-line. So that can happen when you are at t equal to 3. So you have kx, ky, kz, but your co-dimension is 2 or less, right. So d is greater than c. So you have less equation than the number of variables. So for example, let's set t2 to be 0. 0 means it's not even there in your Hamiltonian. Okay, maybe not present is the better word. So the Hamiltonian space is 2 dimensions, and where the top Brillouin zone is 3 dimensions. So let's say d1 equal to t3 equal to 0 at k star. You will find is that so this condition will, these equations will have a solution for 3 variables, but on a contour in which one of the variable. So actually what this tells us is that if you solve for d1 equal to d3 equal to 0, that will give a relation between and without losing generality I am making that equal to, let's say, k star or k 0. Actually it does not have to be 0. So that means it will give a constraint on these 3 variables to make a equation for one variable in terms of other. So what I am saying is, in layman term, that we will have a contour of roots, and that contour is called nodal line or loop. So let us take a 3D. So in this case there will be some line, and if you want to see the band structure, so you can take this line, this is my energy and these are some which may or may not be along the high symmetry points, but if it is not at the high symmetry point they will come in pairs like the Weyl. But here if I assume them to be along the high symmetry line, so it will be along some kz equal to 0, then this will be kx and ky, and then I can remove this. So these bands are degenerate in some contour. Okay, and imagine that doing it in some 3D. You can check it out on some Google search that this will happen in a contour like this. It's called nodal line. All right. So now let's try to see a little more in depth about what is happening in this region, or in this region, or in this region, or in this region, and also talk about the corresponding materials. So we can talk about a tight binding model, and we did talk about two tight binding model in which we saw the Dirac cone, but let us try to come up with something simpler, and we call those K dot P model. So it is a continuum model near the degeneracy, okay, near K star, okay, and one can also call it something like a field theory model, kind of a long wavelength with respect to K star model, okay. So how do you obtain it? So here P is slightly misleading, but we will talk about where does this name come from. So what do? We do a Taylor expansion, okay. So it should be, so let us start with some 2 by 2 Hamiltonian again, and we already said that at K star all the D vector goes to 0, and now we want to expand around K star, some around K star in the K space around some K star. So it should be just be a so this can be slightly confusing. So we are still calling it K with respect to K star, but rather one should call it delta K. So some small wavelength K values with respect to K, somewhere here. Now carrying a delta K is kind of complicated notation, and some people also use it called Q, which is defined with respect to some K star, okay, and everything can be vector. So what we will do is that we will remove the star delta, and we will assume that it is defined around K is a small wave vector around K star. Just a Taylor expansion. Plus y plus z component then half d mu dkx square kx minus kx star and so on, and you will also have terms like cross term and so on. Alright. So, we can identify already what these terms are. This is my velocity, group velocity, velocity at this point, something like a star, and also you can obtain this as the mass along x, effective mass, with h bar set to be 1, and this will be again velocity square, velocity along x and y and so on. So, and this one goes to 0. So, what we have is v mu star q mu, okay, and q mu often I find it confusing. So, what we will do, okay, let me write it and then we will see. So, there are also some sort of a m mu, okay, m mu xx q, okay. So, you can actually have this, and qx or qx square and plus 1 by okay. So, what we do is that we just use simpler notation, and let us call it Vx kx, and often we will use some term, some notation, call it, let us call it alpha kx square plus ky square plus kz square, and you can also have alpha, let us say beta kx ky and so on. So, now near this point generally the leading term contributes, but there can be region, symmetry region or all, that for example odd term, these are odd terms, odd term may not be, if you have inversion symmetry, odd terms may not be allowed, so you will have even terms and vice versa. Okay. So, with this, so then we will do k dx will be linearized with kx, dy will be linearized with ky and so on. So, now remember the example where d1 was or equal to sin kx and probably even t prime if you want to put it. So, that will be like some Vx kx, that is the leading term. The second term will be k cube, which we will ignore. So, d2 will be Vy ky, okay, and it will be V ky will be V kx if V equal to Vx equal to Vy. So, that means it is kind of a circular region, and let us say d3 equal to 0. So, the Hamiltonian can now be written as sigma dot k with some v, and that is the k dot p Hamiltonian. This is like your k, this is like p and this is like k. Okay. So, that gives you a Dirac cone with linear dispersion in some kx ky plane, okay. And the slope tells you the velocity. You can have an anisotropic one in which Vx Vy are not same. Okay. And so this sort of dispersions we get in graphene. We will study this in details, and also 2D surface state of 3D topological insulator and some D wave superconductor. Okay. We will study this one in depth and also this one. And it's sort of easy to generalize for 3D. And then you will have Vx sigma x kx plus Vy sigma y ky plus Vz sigma z kz, and again if it is a symmetric then you will have V k dot sigma or sigma dot k. So, this will give us a 3D Dirac cone. It is linear along all three directions. So, symmetry then has to sort of allow us to have this term vanish, then only the odd term will appear. So, the leading term will be linear, and then the as you move away from the Dirac cone, then k cube term and all will appear. But in some lattice you can also have this term in some complicated way and this term complicated way, they are called warping term. So, that means this Fermi surface, the actual Fermi surface is, and a chemical potential is somewhere here, and these are not really very small k points, and if this is your chemical potential. So, you will have a, you are supposed to get a circular Fermi surface, but these k's are not really small. So, you need higher order corrections. The higher order correction, then you have to worry about obtaining this, which are the warping effect, Fermi surface warping effect. So, you are sort of moving away from the simple circular Fermi surface to a more curved Fermi surface. Okay. And for that the symmetry is very important to figure out which terms are allowed, which terms are not allowed. So, coming back to 3D Dirac cone, and there are also materials in which such Dirac cone has been observed, and Na3 Bi 3As2. Okay. The reference you can find out from there. And so, another point is that for the stability, the Dirac cone, they often come with 4-fold degeneracy. So, these things will give us basically a 2-band model. So, 4-fold degenerate, in which we replace the Pauli matrices with gamma matrices, which are 4 by 4. They are also anti-commute and all. Those details we do not need right now. So, in that case you will have a Dirac cone which is two-fold degenerate here, and each one is again two-fold degenerate. Symmetry is important, which turns out to be time reversal plus inversion. So now, if either time reversal or inversion symmetry is broken, so this four-fold degenerate Dirac cone can be split if time reversal or inversion is broken. Into some different k points. Okay. Then each one then can be written in terms of (2D) Dirac cone, and whereas here it will be minus or and together we can written as and where chi equal to plus minus 1 called chirality. We will study that later. So, these are actually at high energy they can be combined, but near this point these are the minimal Hamiltonian that connects them. So, the typical bases which will give such four-fold degeneracy are 2 orbital 2 spin, okay. But they also have to have some symmetry, so that we can write it in terms of this, and then we have to make some unitary rotation to mix the orbital and spin. So, generally you need to have some spin orbit coupling and go to a total angular momentum basis in which this splitting can be done if there is a something called SU2 cross SU2 symmetry. Okay. We will talk about that again little bit once we cover symmetry. So, these are called Weyl semi-metals. Okay. And there is also now a lot of materials which are so the first material which obtained were inversion broken Weyl semi-metal AS family called AS family tantalum arsenide family, and there are materials which are so you will get a full list in the review article that I gave you at the beginning. Now there are more materials of course. Then time reversal, broken, cobalt 3, tin 2, sulfur 2, Mn3, Sn, Mn3, Ge, Eu, CD, As2. So there are also type 2 and type 1, and in a separate chapter we will distinguish those. Let us just go through this in a coherent way for the time being. So the third one is the nodal line. Nodal loop. Okay. So we talked about that one of them has to be 0 by symmetry, let us say. So we have a 2 by 2 Hamiltonian, but it will be only two term, but in 3D. In 3D. Okay. So again we are making a choice. So let us say D3 equal to some V kz, okay, and D1 D2 has to be a contour, there has to be relations between them, and generally it turns out that you, for symmetry reasons, the linear term won't contribute, it is the quadratic term, and we can take a quadratic term that will be like, let me see which one I take. You can take even more general. So now you can see that so this is kz direction and then kx and ky. So you can see from this expression on the kz equal to 0 plane, this term disappears, So you will have a contour that is defined by this. Let us draw that contour. Which is when kz equal to 0 plane and m equal to b kx square plus ky square, it is defined by this. So you can see that kx, ky are no longer independent variable on this line, and where all the d are going to 0. So to give a constant between these two, it gives a contour, And from this contour, if you look at the bands along the z direction, it will the leading term will be kz. So, we will have a linear dispersions. And if you go this way also, it will be linear. If you go this way also, it will be linear. So, at every point the bands will disperse linearly if I draw the band. And these are called nodal loop or nodal ring. And there are also materials in which such things have been observed, such as Pb, TaAc2, copper 3, PtN, Ca3. Okay. So, these three classes of semi metal then we talked about. One was in 2D, which we call Dirac cone, 2D Dirac cone. Then we talked about 3 dimension, which is just a generalization of it. We will have a 3D Dirac cone. Then if you split a 3D Dirac cone, which has a 4-fold degeneracy, into each 2-fold degenerate Dirac cone, we call that Weyl semi metals. And then we also talked about a nodal line semi metals, in which you will have a contour of degenerate point. We will not be able to talk about in all these 3 classes of material in depth, but in the next class we will start with the first one, the 2D materials, which was first realized in graphene. So, we will start with the graphene having a Dirac cone, then we will open a gap to make it a Chern insulator called Holden model. Okay. Thank you very much for your attention and see you in next class.